it seems to work, yeah. And so, of course, the very first thing to say is that this work is a collaboration, and it's actually based. The main results will be based on the experiment performed in Freiburg, here on lithium barium plus, and we collaborated quite a lot with Pascal Wekesser and Fabian Tillemann on these results. And it comes out mainly from the PhD thesis of Xiaodong Xing, and this is the work performed in collaboration with colleague in Orsay here. Yes. So in terms of motivation, I think there is not too many things to say, as the program of the workshop says it all. And these are all the keywords that you can grab from the title and the abstracts of the workshop, and you have seen already one of them here. And the thing is that in many respects, all those topics are really also challenging for theorists, as you will see. So we have seen a few theoretical determination in Stefan's talk, and I will also present some, as you can imagine. Here is some kind of, some of you may have seen already that slide, and hopefully it is almost updated. If not, we'll be happy to hear. I even put this one here from Carlos here, this kind of new developing trap in Florence. And yes, so this is thing, and all that kind of combination. And the statement is that despite this apparent simplicity of the system, actually there is kind of a complex dynamics taking place in these experiments. And so there are several reasons for that. There are many excitation channels because there are many lasers which are involved in the experiments. Beside the fact that we have only a two-body system, the structure could be kind of complex, depending on the level of precision you want to look at. One of the goals is, of course, and the objective is to prepare the colliding partners in a single quantum level. We heard also, and we will hear also in the program, in the workshop, that of course those experiments now enter the S-wave regime, collisional regime, with the observation of Feshbach resonances, three-body combination. And the thing is that this list is not just zoology, but actually the various atom-ion combinations offer various opportunities for different types of behavior. I mean, the process which are in competition are not the same depending which species you select. It's some kind of a knob that you can use for the experiment. I mean, it is more complicated than the knob, obviously, but I mean, it is really worthwhile to look at all those systems. And so one of the main reasons at the very beginning, when you start that kind of experiment, is that there is an inherent complexity, which is that the laser cooling of the alkaline earth ions involve a metastable state. So here I just picked a few schemes in these papers for calcium plus, strontium plus, barium plus, and ytterbium plus, if you allow me to call that an alkaline earth ion. And so every time there is a metastable state here, and which means that if you don't pay attention to that too carefully, then of course it is involved, this state, it will react with the neutral atoms which are around. And so they take part of in the dynamics. And actually this kind of story started quite long ago, like more than 10 years ago, with a collaboration that we started with Stefan at that time on this calcium plus rubidium. And we did not actually really address that problem directly, but there were already several channels involved. And actually in that paper, this is where we kind of elaborated on the fact that the results of those kind of observations, of those kind of collision between atom and ions, were actually strongly influenced by the light which were in the experiment. At that time, 10 years ago, it was not so obvious. And so we kind of designed a theoretical model for that, and there were those channels where the ion is either in the ground state, the metastable state, or the excited state here by laser excitation. And here we actually discussed only qualitatively the fact that starting from here, there should be no charge exchange in this particular case, only excitation exchange. And so with a fairly low reaction rates, but it was like a qualitative discussion. And yeah, and so it has been a bit elaborated in that paper here. Then, at the same time, we looked also into rubidium barium plus experiment, also in the same way. And so we were also, again, qualitatively, but we are also with that kind of calculation again. You see, always you have all kind of potential energy curves here, and you have a lot of dissociation limits, and then a lot of possible interactions. So it's quite kind of complicated. And and here in this particular case of rubidium barium plus, presumably when you start from this barium plus 5D, there are not too many channels also to interact and to generate charge exchange. And again, it is still qualitative, but just to say that looking at the curves, we can already have some kind of feeling about what could happen in that kind of system. Here, I just want to mention that this system has also been explored in Freiburg and in Ulm, and maybe we'll hear a bit about those work, and I just put a reference here for completeness. And here, actually, this is where we had the chance to collaborate with Rui here on this particular system. And again, this is the same kind of thing. So you may think that all those graphs, they just look the same. In a sense, yes, they are all complicated, but every time you have tiny details depending on the channels which are involved. And here again, we start, if they start from the metastable state of strontium plus, and then you can have here excitation exchange and maybe charge exchange here. And but here we discussed that particular process in this particular case more quantitatively. Actually, I was presenting those results at the last ECTI conference in Israel. And the thing that that kind of calculation actually provide and results, they provide strong constraint on the computed PECs and potential energy curves and also dipole moments and all kind of stuff, and also on the dynamical models. And at that time, actually, we used a model which was kind of too simple. And despite the fact that we have some kind of qualitative feeling about what's going on here, you see you have this entrance channel which is crossing kind of some curves. And so you may expect some outcome here. But still, we are not able to reproduce at that time the experimental results in terms of output products, outgoing products. And this is the paper here. And actually, I've seen that paper from last year, but I have to confess that I have not taken time to look to which extent those cross-sections were updated and to see if there were some kind of difference discussion to have with our results. Yeah. Then also this kind of situation, we also had the chance to collaborate with people in Osaka, and again, so here we enter to these kind of systems, which could be more interesting in terms of entering the SOF regime, because we have the lightest possible atom here with some kind of more heavy ion, and then which is expected to be more interesting in terms of going to lower temperature. And here again, due to the fact that we have this metastable state, then we may have some kind of interaction here again, which would produce some charge exchange. And here also in that particular paper, we made also some kind of qualitative model, which were kind of saying, hey, we should indeed have efficient curve crossing and then charge exchange, but we did not complete a full calculation. Okay. By the way, in all those cases, I'll always put that number, which is the energy difference between the incoming channel and let's say the closest outgoing channel. And this is interesting because if some ion is produced here, would produce by charge exchange, actually it would be some kind of hot ion, and which is indeed detected in the experiment. The fact that you can produce a hot ion could be indeed detected, and then it is kind of a signature of that kind of reaction. So I don't enter into those experimental details. Hopefully there will be some occasion to hear more about them in the forthcoming talks, but just to say that each time you have some kind of really large amount of energy which is liberated, and then as you can imagine, that is really a very strong perturbation for the experiment, aiming at controlling what's going on with these atomic ions. Okay. So actually, you can look. This is some slide which is really a bit old, it is a bit a pity because actually we made all those calculations, but we never published them, by themselves. So that's always too bad having that in the drawers. But still, anyway, you can having this series, for instance, with calcium plus, where you see that depending on the combination, either you have charge exchange or excitation exchange, which is the main process which is allowed, and then with various amount of liberated energy, either small or big here. And also we made the similar kind of analysis with the strontium plus compounds here. And here I just put the figure for the silicium strontium plus. So all those things are more or less in our drawers in a way, but just to say there are plenty of possibilities to look at carefully at that kind of dynamics, and again to look at the quality of our theoretical calculations here. Okay, so you see, again, they all look the same, but there are very differences. That if you zoom on those things, you have real differences depending on the molecular symmetry which are involved, and then which are expected to provide some efficiency or not for that kind of processes. Okay, here, so let me present in the remaining time a full application about the last development that we made for then the case of lithium barium plus. And here again, same kind of figure. And actually, the originality of that particular system, and I think it is shared also by the lithium ytterbium plus experiment, is the fact that it is one of the early systems for which the entrance channel with the lithium in the ground state, the ion in the ground state, is indeed the ground state, the absolute ground state of the system, which is not, it was not the case for ytterbium. I was kind of, yeah, thanks for, it was confusing. This is why I say maybe, but thanks for the correction. So yeah, so it is the case for lithium barium plus. And so in a way, so there you do not expect to have lower channels, lost channels here. So this is the interest of that particular one. And so again, here you have the possibility to have this metastable state. And when you look into this picture, you already see that you have an efficient volume crossing between those two states here, singlet sigma plus, here, which is here. But it is not the whole story, because in principle, if you really want to have the full picture, you should also consider the spin-orbit interaction and so on. But from the very first step, you can say that there should be already some kind of non-radiative charge exchange occurring in that particular system. And so the experiment, so I just display the final result that they got without giving any details about the experimental setup by itself. So the thing is that they had the possibility to prepare the ion either in the D3 half states or the D5 half state here. And each time they look at some interaction time, and they look at the decay of the ion as a function of time. And this time is actually converted into the number of Langevin collision. That is that when you do the density of the atom, that you can deduce some kind of Langevin rate for those collisions, which means that you, in a way, you can tell how many Langevin collisions you had in time, and to see indeed the decay of your ion, and then you can extract from that decay rate to be compared to some theoretical model. And so these results are actually extracted from the PhD thesis of Pascal Wekesser last year. And then in a way, almost the final statement here is the following: when you introduce, and we'll see how the fine structure interaction, the spin-orbit interaction in this picture, what you can see is that you have the possibility to have three competing processes, which would be this kind of fine structure excitation quenching here, going from this channel to this channel, or the non-radiative charge exchange, and maybe also the non-radiative excitation quenching going down to the ground state. So in principle, all those processes could be possible, and see what is the result actually. And maybe we'll hear more about that kind of these experiments in that talk later today. Yes. So let's see how we do that. So it's again, it is the very first step is to go through the molecular structure. So these are our potential curves here, And I take this opportunity to say that actually Michael Groups has calculated those potential curves in the same time, and also for highly excited set, and it looks, I've not made a very detailed comparison, but the overall agreement seems to be extremely good between all our calculations. And so, as I said, we want to model we model the system with this Hamiltonian here, where we have the kinetic energy. So this now for the collisional scattering model, the dynamical model. When you have the kinetic energy term, we have the potentials. And as I said, we want now to include the spin orbit term and also the rotational excitation. And so, as I said, this is coming from the recent thesis in our group. And here it is actually a new calculation that we have made. So I will not put too much details on these particular calculations, but typically we are able to calculate molecular spin-orbit couplings here by using some kind of new, I say new because actually the ideas are actually quite old, but it has been used already for in this particular paper, to my knowledge, a new quasi-diabatic approach, which is based on the fact that we can design an effective molecular Hamiltonian from the molecular one, from this one, which is rotated in some kind of approximation of an atomic basis sets, atomic space, say, and then which we can use now that we have we're in some kind of atomic representation. We can directly use atomic spin-orbit matrices instead of using any kind of effective expression for the molecular spin-orbit Hamiltonian. We can directly rely on atomic spin-orbit matrices, and then by performing the transformation, that transformation back to the molecular approach, then we can extract R-dependent spin-orbit coupling for all kind of molecular symmetries that we have. And here, all those lines corresponds to the either diagonal elements or off-diagonal elements, spin-orbit elements for this interaction here. And you see, you have depending on the situation, you have quite brutal variation of those couplings depending on the distance. Just to say that starting, you see, this is basically the atomic spin-orbit couplings, but once you enter let's say that kind of range where you have exchange phenomena starting to be dominant, then you have significant variation of the molecular spin orbit. And because the dynamics is located exactly in that kind of range, then it is really important to model them in the right way to have efficient quantitative comparison in dynamical models with the experiment. Okay, so this is I would say the main new data that we have here. And then again, what we have made actually, what our students made here is actually to try to elaborate theoretical models from the simplest one to the more complex one. So the simplest one was some kind of multi-crossing Landau-Zinner model. And here you see those channels, only these 4 channels which are here, and with the blow up of this one here. And by using this Landau-Zinner model, and these are just the very conventional probability that you can get when you cross those various crossings here. So I don't go into the details, but these are just some kind of analytical evaluation of those probabilities. Then you can already model what's going on and what's going out in those various outgoing channels. The point is that here I don't put numbers, but we're only able to obtain qualitative agreements in terms of the efficiency of these multiple crossings, but the numbers that we get from this very simple-minded view were really off compared to the experimental findings. So then we went to the next step, which is just doing a real scattering calculation, because we know that this Landau-Zinner model is just too elementary. And when we made some kind of quantum dynamical scattering model with the same 4 channels by computing conventional scattering cross sections by using the scattering matrix elements, which are resulting from the coupled channel calculations, which are solved numerically. Here, actually, this calculation, you see that this is the partial wave, so which means that in a way, this calculation in that particular case are made in the molecular frame. That is the way that it is not coupled to rotation. And so, as expected, for this kind of ion atom collision, we obtain rates which are almost constant. Here is the Langevin rate, and here are, for the various channels, almost constant rates. And you can already see that from those quantum dynamical calculations that you may see shape resonances coming in, By the way, the dashed lines are a non-thermalized rate, and when you thermalize it, when you use some kind of thermal distribution of the atom and the ion, then you see some kind of those shape resonance are kind of flattened. And so this is what we get, but and this is some kind of a hierarchy that we get in terms of the processes. Here you see the various rates for those various processes. But the point is that if we translate this curve into number, this is what you get. So here is the result from the experiment. So as I said, in the experiment, they count, they see the number of ions that they get, either hot ions or the loss of ion itself, which is associated to one of those processes here. And they have counts in the experiment here, and when they compare to the initial population of the baryon plus ion, and then to the Langevin rate, they're able to extract this data, which is the ratio between the experimental rate compared to the Langevin rate, which provide that kind of number here for the experiment. And you see, with this kind of simple model here with only 4 channels, we get some kind of, yes, qualitative agreement, but it is not at all perfect. In particular, the hierarchy between the processes is not really good. So it means that we have to go yet one step further. And here now we have done this multi-channel scattering model. In other words, we have calculated this, we have done this calculation in the lab frame. That is that now we are coupling to the rotation, the material rotation of the ion and the atom, okay? And which means that in this calculation, we put now 3 dissociation limits, the 3 lower dissociation limits, 9 molecular states, R-dependent spin-orbit couplings, the rotation couplings, which means that at the end you have a 16 by 16 matrix to run your dynamical calculation. And you have to pay attention to be very cautious when you do this basis transformation from the body fixed, that is the molecular frame, to the space fixed frame, which is here expressed in terms of going from one set of quantum numbers to the other. And then you have to perform this angular momentum algebra, which look like obvious, but when you want to implement that in a code, then you have to be extremely cautious with that. And then once you have done that properly, then you have again the expression of the cross section here now with respect to the total angular